Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Vapor Liquid Equilibrium Part 2. It is a continuation of our previous lecture. In the previous lecture, we have discussed several aspects of vapor liquid equilibrium, especially when both the phases are obeying a kind of ideal behavior. So, phase diagram, how to do the dew point calculations, bubble point calculations, etc. those things we have seen. Now, in this lecture what we will be doing, we will be taking the same vapor liquid equilibrium case, but when one of these phases exhibit as some kind of non-ideality, right, or both the phases exhibit some amount of non-ideality, then how to bring in the non-ideality of either of the phases in the equations, and then how to solve those equations in order to get the equilibrium composition of a multi-component mixture when these phases obey non-ideality. So, that is what we see. So, now what we do, first we start with a kind of non-ideality in liquid phase only. That is, we take a low pressure case, so that the vapor phase still be behaving a kind of ideal, but the interactions among the molecules in the liquid phase are not similar to each other for different possible interactions. So, that liquid phase is showing a kind of non-ideality. That case we will be taking first. So, equilibrium between non-ideal liquid and ideal vapor phases. Real system does not follow Raoult's law, since it is unlikely that AA interactions are quite identical to AB interactions. That is not possible in general. Actually, this Raoult's law, what does it mean? It says that a liquid is ideal in the entire range of xi varying from 0 to 1, right. Actually, Lewis-Figasti rule says that the liquid obeys the ideal behavior in the limit xi tends to 1, whereas the Henry's law says that liquid obeys the ideal behavior in the limit of xi tends to 0, whereas the Raoult's law says that liquid obeys the ideal behavior in the entire range of xi from 0 to 1, right. So, when you are saying for the entire range of xi from 0 to 1, if the liquid is showing ideal behavior, that means indirectly you are saying that the like interactions and then unlike interactions are similar. Then only it is possible that liquid is or liquid solution, liquid mixture whatever is there, that can be ideal only when like and unlike interactions are quite similar to each other for the entire range of xi. That then only it is possible, but that is not true in most of the cases. In many cases it is not possible that in the entire range of xi that liquid may be showing ideal behavior. That means in the entire range of xi, whatever the like interactions or AA interactions and unlike interactions or AB kind of interactions are there, they cannot be quite similar to each other in the entire range of xi. So, that means obviously that liquid will start showing some kind of non-ideality. So, now what we do, we take a low pressure for vapor phase. For the vapor or gas phase, if the pressure is low, then we have seen that the vapor or that particular gas phase whatever is there, that would be displaying a kind of ideal behavior, right. So, directly taking non-ideality of both vapor and then liquid phases may become mathematically complicated to solve the problem. So, that is the reason we are starting with this case, where we are taking the vapor phase is ideal, and then in order to have a vapor phase ideal, what is the essential criteria that you should maintain in the operational conditions, that your operational pressure should be low. If your operational pressure is low or system pressure is low, then you can say that your vapor phase is ideal. That case we will take, but we will be exploring the cases for the liquid phase, two different cases when like interaction, that is AA interactions or BB interactions or both of them are stronger than the unlike interaction, that is AB interactions. So, if like interactions are stronger, then we call it positive deviation from ideal behavior, okay? And under such conditions activity coefficient is greater than 1 in general. So, that is what we see. So, why it is greater than 1, what happens under these conditions, etc., those things we will take. And then we will also take the case where the like interactions like AA interactions or BB interactions or both AA and BB interactions are weaker than the unlike interactions something like AB interactions. So, under such conditions the activity coefficient in general is less than 1, and then we call such kind of system deviating negative deviation from ideal behavior. Okay. So, either of the cases we will take and then see how to solve the problems. If the liquid phase consists of chemically dissimilar species and the LR reference state is taken, then we have already seen that YIP is equals to Xi gamma I Fi naught, and then chemically dissimilar species, and then we are taking LR reference state. So, then we know that Fi naught, whatever Xi gamma I Fi naught is there, Fi naught should be F pure I if you take LR or the Lewis Randall reference state, and then F pure I is nothing but PA sat if pressure is low, right. So, that is what we have already seen in the previous lecture. Only additional thing compared to the previous lecture is that now there is a non-ideality in the liquid phase, and then that non-ideality has been brought in terms of gamma I. Okay. This problem now we explore in detail in order to find out equilibrium composition Y I versus X I, let us say if pressure and temperature are given. Okay. So, now for a binary mixture, if you write this YIP is equals to Xi gamma I Pi sat for a binary mixture of A and B components, then we have YAP is equals to Xi gamma A Pi sat, then YBP is equals to XB gamma B PB sat. If you add them together, YA plus YB multiplied by P is nothing but P is equals to XA gamma A PA sat plus XB, we can write it as 1 minus XA gamma B PB sat. So, this you can write XA multiplied by gamma A PA sat minus gamma B PB sat plus gamma B PB sat. So, now from this equation Xa you can find out if your pressure and temperature is known by Xa is equals to P minus gamma B PB sat divided by gamma A PA sat minus gamma B PB sat. By using this equation you can find out, right. If Xa is known, then simply Ya is nothing but Xa gamma A PA sat divided by P. If Xa is known, then gamma A is also known. So, that can be found, right, provided that constants of of the constants associated with the excess Gibbs energy for that liquid phase are known, right. So, then gamma A is also known, that means if you know the Xa. So, Xa gamma A PA sat by P, if you do, you know the Ya as well, right. So, this is what this equation you can use for finding out Xa to find in order to find out Ya. Okay. So, Yb similarly is nothing but Xb gamma B Pb sat by P, that is Xb gamma B Pb sat divided by this 1 minus Xa I am writing 1 minus this Xa I am writing 1 minus Xb gamma A Pa sat plus 1 minus Xa I am writing Xb gamma B Pb sat. So, these two equations can be used find out Ya or Yb or both one. So, these two equations can be used to find out the vapor phase mole fraction. So, Xa, as I already mentioned, you can find out from this equation, that is P minus gamma B Pb sat by gamma A Pa sat minus gamma B Pb sat. Similarly, Xb you can find it out as by rearranging this equation in terms of Xb, then you will find Xb is equals to P minus gamma A Pa sat divided by gamma B Pb sat minus gamma A Pa sat, right. So, these are the equation one can use to solve the problems in order to get the equilibrium composition of vapor liquid equilibrium case, especially when liquid phase displaying some amount of non-ideality, whereas vapor phase being still ideal because the pressure is low, that case we have taken. So, now what we do? We have taken the non-ideality in the liquid phase. So, for the liquid phase non-ideality can be represented by two cases, gamma I greater than 1, that is positive deviation from ideal behavior, or like interactions are stronger than the unlike interactions. So, that case we will take and then see how the calculations can be proceed. So, from Gibbs-Duhem equation, that is x a d ln gamma a plus x b d ln gamma b is equals to 0. From this equation, if you know that because x a x b are less than 1, okay, or at the max they can be 1, right. So, from here if you have gamma a greater than 1, so this equation, from this equation you also realize that gamma b should be greater than 1, right. So, what does it mean by, let us say for binary mixture, when both the phases are displaying ideal behavior. So, in the previous lecture we have seen this equation, that is YAP plus YBP is equals to P is equals to XA PA sat plus 1 minus XA PB sat. Now, for the today's case where non-ideal liquid phase is there, vapor phase is still ideal, but the liquid phase is non-ideal, and then that non-ideality also we have taken that gamma A is greater than 1. Then the corresponding equation in the previous slide we have written this one, that is YAP plus YBP is equals to P, that is equals to XA gamma A PA sat plus 1 minus XA gamma B PB sat. So, now here gamma A and then gamma B are coming into the picture because liquid phase is non-ideal. And now we have seen here for a given temperature this PA sat, PB sat are anyway constant. Now, what we do, we see the pressure, how are they for ideal case, that is when both phases are ideal, and then one phase is ideal, other phase liquid phase is non-ideal, then how the pressure would be different for the by comparing these two equations, that is what we can understand. So, at a given temperature PA sat, PB sat are known, and in general they are positive, okay, and then XA and 1 minus XA are known kind of thing. So, now whatever XA PA sat and then 1 minus XA PB sat are the values it is having, if your gamma A is greater than 1 and then gamma B is also greater than 1, then you can realize that for this second case where the liquid phase is having non-ideality, the pressure, the total pressure is going to be higher than the corresponding pressure in the its ideal liquid phase counterpart. So, that means in this case whatever the pressure is there in the ideal behavior case, that would be smaller than the pressure in the case of this non-ideal liquid phase, provided this gamma A is greater than 1. If gamma A is greater than 1, then gamma B will also be greater than 1 for the binary mixture according to Gibbs-Duhem equation. So, what does it mean? So, if you remember that PXY diagram that we have seen in the previous lecture, P XA versus YA if you draw. So, what we have seen a kind of a PXA curve like this, and then PYA curve like this. This is what we have seen. This is for ideal liquid, this is for the ideal liquid phase. But now what happens in this case, if pressure is going to be more if the liquid phase is showing non-ideality, and then that liquid phase non-ideality is having such a way that like interactions are stronger, that is gamma I is greater than 1. So, the pressure is going to be higher than the corresponding pressure of a ideal liquid phase. So, then obviously this corresponding PXA curve for this case is going to be like this. It is not going to be straight line like in the previous case that we have seen. So, that is what it means by, right. So, in the Raoult's law, when the liquid phase is also ideal, so then we have a PXA curve as a kind of straight line, right. But in the case of non-ideal liquid, this PXA curve is not going to be straight line, because in this case we have taken like interactions are stronger. So, then gamma A, gamma B both are greater than 1. So, the corresponding pressure here is going to be higher than the its counterpart ideal liquid pressure, right. This is what, let us say what happens if the like interactions are weaker or gamma I is less than 1. So, then from this equation, if gamma A, gamma B are less than 1, so for a given XA PA sat combination and then XB PB sat combination, the corresponding pressure that is going to have here in the non-ideal liquid is going to be lower than its ideal counterpart. So, that means under such conditions we may have the curve Pxa curve like this. So, this is again Pxa curve, but gamma I less than 1, and then this is also Pxa curve, but gamma I greater than 1, whereas the solid straight line is also Pxa curve, but gamma I is equals to 1, that is ideal liquid. So, that is the difference that you can realize from here. Okay. So, from above two equation, for a given mole fraction of species, system will exhibit higher pressure than its ideal counterpart, because first case we are taking gamma A and gamma B both are greater than 1. Okay. So, such systems are known as systems with positive deviation from ideal behavior or positive deviation from Raoult's law. Okay. From a molecular standpoint also these results make sense, because what happens at a given temperature, the molecules in the liquid have a fixed kinetic energy. However, the unlike interaction in the liquid are not as strong as the like interactions. Let us say any solution, liquid solution, pure solution, if you take, the like interactions are going to be very strong in general, right. But if you add some other component to this pure component, then there will be unlike interactions as well. In addition to AA and BB kind of like interaction, there will be a kind of unlike AB interactions would also be there. But the case is that in general the AA interactions or BB interactions are going to be much stronger than the unlike AB interactions, right. So, if the unlike interactions are not stronger, then obviously its tendency to escape from the liquid phase and to join or go into the vapor phase is going to be very high compared to the case of pure liquid cases. Okay. So, that is what it means by. So, the unlike interactions in the liquid are not as strong as in the like interactions. Thus, two species when mixed are not held as vigorously in the liquid phase as they are in the pure solution form, pure form before adding together or before making a kind of liquid solution. Therefore, more molecules escape to vapor than in the case of an ideal solution, and obviously pressure exerted is higher. If more and more molecules are going into the vapor phase, then obviously the pressure of the system is going to increase gradually, right. And then because of that one, whatever that Pxa curve that we have seen, that is going to have a kind of a pressure showing higher than the corresponding pressure by ideal behavior. Okay. So, one example we are showing here, positive deviation from Raoult's law, methanol and water system. If you take at 323 Kelvin, then it will be showing positive deviation from Raoult's law. So, corresponding Txy plot also we have shown at 1 atmosphere for the same system. So, the previous one whatever I have shown, it is shown here. So, the Raoult's law, if it is exhibiting methanol water system, then we have this straight line where gamma I is equals to 1, right. So, if the system is having positive deviation from Raoult's law, then because of that non-ideality, whatever the molecules are there, they are having more tendency to go into the vapor phase, and because of that one pressure increases, and then whatever the deviation is there, that deviation is called as a kind of positive deviation from Raoult's law. So, that occurs when gamma I is greater than 1 or positive deviation like this. Okay. Rest everything is same as we have discussed in the previous lecture, that above this Pxa curve we are having subcooled liquid, and then below this Pya curve we are having superheated vapor. In between these two curves, whatever the enclosed area is there, that is the region where both vapor and liquid are coexisting and they are at equilibrium. And then this curve Pxa curve is also known as the kind of bubble point curve, because that is the point at which first bubble forms from the liquid states as you gradually decrease the pressure. And then this Pya curve is also known as the dew point curve, because when you gradually compress the vapor by increasing the pressure at constant temperature. This is the point, this P by A curve is the point lying on this P by A curve would be the one at which first dew point is forming, first dew is forming from the superheated vapor. So, that is the reason it is known as dew point curve, that P by A curve also. Whatever the P by A curve is there, that is also known as the dew point curve, right. So, rest everything is the same, only thing that we have this gamma I is greater than 1. So, accordingly there is a kind of a higher pressure compared to their corresponding ideal liquid case. Okay. So, we have not seen any Txy plot. So, for a comparison purpose, I have shown the Txa plot of the same methanol water system, but at 1 atmosphere. So, temperature versus Xa Ya is shown here, right. So, here, so since it is Txy curve, so the vapor phase would be at having the vapor phase will form at higher temperature. So, then the above curve whatever is there, that is known as the Tya curve, whereas in the Pxa curve it is below curve, whatever the below line is there, that is Pya curve. And then liquid phase would be existing at the lower temperature, that is the reason Txa is a below curve, whereas the liquid phase at fixed temperature will have at higher pressure, by gradually increasing the higher pressure. At that time we will be getting the condensed phase or compressed liquid phase that you can get, that is the reason that Pxa is there. And then here this is known as the Pbsat in Pxa curve, and then this is known as the Psat corresponding values. But whereas here, now here it is nothing but boiling point of A, and then corresponding this value whatever is there, that should be boiling point of component B. So, now methanol water boiling point is 100 degrees centigrade. So, then that is the reason 373 Kelvin here is shown as the kind of boiling point of that point. So, this Tya curve whichever intersects upper end of y axis is it is a boiling point of component N, wherever the lower end of Tya curve intersecting with this y axis is known as the other side of the y axis is known as the boiling point of component B, right. So, now in between we have a kind of between these two curves, whatever the enclosed area is there, that area it is both having both vapor and then liquid phases, right. Above this Tya curve, now we have the superheated vapor, right. And then below this Txa curve we are having subcooled liquid, and rest everything is same as in corresponding Pxy diagram, because here now here this is, let us say, tie line if you take. So, this is the at constant temperature it is joining or tying up the two compositions of equilibrium phases, that is Ya and then Xa correspondingly. Okay. So, similarly here also we can find out what is the bubble point composition, dew point composition, etc. All those things we can find out from Txy diagram as well as we have done from Pxy diagram in the previous case. Okay. So, this is about the positive deviation from ideality or positive deviation from the Raoult's law. So, what if we have a negative deviation? Negative deviation from Raoult's law can be plotted in a similar way, where Pxa line will be below RL line in negative deviation from RL assumption, because whatever that equation if you write, P is equals to Xa gamma A Psat plus 1 minus Xa gamma B Pbsat. So, now if gamma A is less than 1, gamma B is also going to be less than 1. So, then whatever the value of Xa Psat and then Xb Pbsat are there, if you are multiplying these two individual terms by some number which is having less than 1. So, the overall pressure is going to be less than its corresponding pressure, whatever the ideal pressure or the ideal case pressure, that is x A P A sat plus 1 minus x A P B sat. So, compared to this one, in this case it is pressure is going to be less because here gamma I is less than 1, negative deviation from ideal behavior, right. But such cases are very rare because we know that the like interactions, that is AA interactions or BB interactions, or both AA BB interactions are stronger than the unlike interactions, something like AB interactions in general for most of the cases. That is the reason, the tendency of the molecules to escape from the liquid phase is higher to go and join the vapor phase, right. There will be very rare cases that the tendency of these molecules, the tendency of these molecules would be less and then bind together with some other foreign materials much stronger. That is, the unlike interactions being strong is a very rare case in general. However, there are a few systems. So, for example, if you take tetrahydrofuran in carbon tetrachloride at 303.15 Kelvin, then we can have negative deviation from Raoult's law like this. So, now here pressure versus P versus x1 y1, if you do, this is the case P x1, but gamma I is equals to 1. Now, here this case, this curve whatever is there, this is nothing but again P x1, but here gamma I is less than 1. That is the reason the pressure is less than the corresponding ideal liquid pressure, okay. And then this other curve is like P by 1 curve, right. Below this P by 1 curve, what we will be having? We will be having a superheated vapor, because it is a PXY diagram, and then above this PX1 curve we will be having subcooled liquid, and then whatever this enclosed area between this Px1 and then Py1 is there, that is the region where both vapor and then liquid phases are coexisting and they are at equilibrium. Okay. Similarly, for a multi-component mixture, when vapor phase ideal and then liquid phase is non-ideal, then we have this equation, we can extend it to the multiple component mixture having m number of components, then YAP you can find out from this equation like this, right. So, now what we do, we take an example problem, dew point calculation of a non-ideal liquid with T known. A binary vapor mixture contains 48% ethanol in water at 70 degree centigrade. So, T and Yi are given. Determine the pressure at which this vapor develops the first drop of the liquid and what is its liquid or dew point composition. Okay. So, pressure at which first drop of liquid forms from this vapor mixture, and then what is the corresponding composition of that liquid drop, that is xi, P xy we have to find out. The excess Gibbs energy can be described by 3 suffix Morgul equation with parameters A and B given like this. Okay. For the liquid phase, it said in the problem it is mentioned that 3 suffix Morgul's equation is sufficient to display, or the is 3 suffix Morgul's equation is sufficient to represent the non-ideality of the liquid phase. That is what mentioned in the problem, but about the vapor phase it is not mentioned, and then we cannot know whether it is ideal or non-ideal because the pressure is also not known. So, under such conditions we have to make some kind of adjustments, assumptions. One assumption is that no details are given, so then you can take the ideal behavior, but logically also we have to think how it is possible, is it going to be, that assumption is going to be reliable or not. So, then what we have to see at this 70 degree centigrade, because the system is at 70 degree centigrade, at 70 degree centigrade we can know the vapor pressure of this pure component ethanol and water, and then in general at 70 degree centigrade the vapor pressure of these two components is below 1 bar. If the vapor pressure is very small, then it is possible that the vapor mixture that is formed because of these two component is going to be having the pressure smaller pressure, and then pressure is small. So, then we can take ideal gas assumption without any difficulty, and then that will not induce much error at all, right. So, if the vapor phase is ideal, then we have YAP is equals to XA gamma A PA sat, YBP is equals to YBP is equals to XB gamma B PB sat. So, that generalized one we have written here. Okay. So, gamma I, that 3 suffix Morgul's equation we have to use, that is given. Okay. So, for 3 suffix Morgul's equation, ln gamma I is nothing but A plus 3b by RT xj square minus 4b by RT xj cube if it is ij mixture of ij and component. If it is mixture of 1 and 2 component, then ln gamma 1 is equals to A plus 3b by RT x2 square minus 4b by RT x2 cube. Similarly, ln gamma 2 is A minus 3b by RT x1 square plus 4b by RT x1 cube. Now, here this equation if you wanted to solve, right, because this equation you need to know what is xi. So, xi is nothing but simply YIP divided by gamma I PI sat, and then P is nothing but summation of xi gamma I PI sat, right. So, that P is not known and then xi is also not known. So, then until and unless you know xi, you cannot know the P, right. So, we will see how to solve this problem. So, but we have to go step by step. So, gamma I can you calculate, because A and B are given, T is given, but xi is not given, that is x1 x2 is not given, right. So, we have to write this equation for 2 component system and then see if we can overcome this difficulty. So, this equation, whatever equation number 2 we have, this is your equation number 1. So, whatever the equation number 2, that is 2a 2b, gamma 1 is nothing but exponential of A plus 3b by RT x2 square minus 4b by RT x2 cube, this is gamma 1. Similarly, gamma 2 is exponential of A minus 3b by RT x1 square minus plus 4b by RT x1 cube. So, this if you substitute here in equation number 1 in place of gamma I, then we have P is equals to XA, P is equals to x1 for because we are having the labels 1 and 2 for these components. So, if you substitute equation 2 in equation 1, then P is equals to x1, in place of gamma 1 we have written this one P1 sat plus x2, in place of gamma 2 we have written this one P2 sat. So, now here in this equation A, B are known, temperature is given, P sat you can find out because temperature is given, then P sat can be known from Antoine equation. If it is water, then from steam tables also we can know what is the saturation pressure of that water system at T is equals to given temperature of 70 degree centigrade. It is given as 70 degree centigrade. So, those things are known. Only thing unknown is x1 or x2 here in the right hand side, but left hand side P is also not known. But left hand side P is also not known. So, we cannot solve this equation directly. So, what we do? We write expression for yi is equals to xi gamma I pi sat by p, right. Yi is given. So, y1 if you write y1 is equals to x1 gamma 1 p1 sat by p. So, then you have this equation x1 and then this particular thing is nothing but gamma 1 P1 sat divided by P is nothing but this equation number 3 from P, we are having P is equals to this one, right. Similarly, for y2 also you can write like this, but now this equation we see left hand side y1 is known, right hand side a, b, t are known, P1 sat, P2 sat you can know from the Antoine equations or steam tables. So, only is unknown is the x1 or x2, that is 1 minus x1. So, in this equation for ethanol, that is for the first component, Antoine constants A, B, C are given here. So, by using Antoine equation you can find out the saturation pressure of first component as 0.72 bar, and from the steam tables for water at 70 degree centigrade you can find it out P2 sat as 0.31 bar. So, P1 sat, P2 sat is also known. So, everything is known in equation number 4 except x1 or 1 minus x1 in place of x2. So, that you if you substitute these values, right, y1 is equals to 0.48 and then P1 sat is 0.72, P2 sat is 0.31 and then A and B whatever given values, and then T 70 degrees centigrades etc., that you substitute in equation number 4, you will get after simplification x1 as 0.12. That means, if you x1 is known, then x2 is also known as 1 minus x1, that is nothing but 0.88. So, both x1 and x2 are known. So, these values if you substitute in equation number 3 along with that A, B constants, P1 sat, P2 sat and temperature, and then solve, then you will find it out. The pressure P is going to be 0.55 bar. Okay. So, by comparison experimental results for this system is that P is 0.57 bar and x1 is 0.13, and then we can see that it matches really good with experimental results, right. That means this 3 suffix Morgul's equation is much reliable to reproduce experimental results for such kind of systems like water, ethanol, etc. Okay. Now, we have a algorithm for dew point calculation of non-ideal liquid and non-ideal vapor phase also. I am directly saying the algorithm because when both vapor and then liquid phases are having non-ideality, that means we are working at high pressure systems, then what happens, the equation should become more complicated and then one has to go for a kind of iterative calculations as we are describing now. So, this is the other extreme case of both the phases displaying ideal behavior. Now, in this case we are taking non-ideal behavior for both vapor and liquid phase. If you are saying that vapor phase is non-ideal, that means by default you are saying that pressure is not low, pressure is high. So, that you cannot avoid the non-ideality in the vapor phase. So, when you say the non-ideality is there in the both phases, you have to depict or you have to show or represent the equation by which the non-ideality of each phase is represented, that you have to mention. So, what we do, we take a case where the vapor phase non-ideality is represented by van der Waals equation, because such equations we have extensively used in previous lectures where we wanted to find out the Figasti or Figasti coefficient, right. Because now vapor phase is also non-ideal, so we have to have the information about the Figasti coefficient as well. And then for the liquid phase, what we do, we go by the 3 suffix Morgul's equation, which we just now found, we just now have used. Okay. Then we assume that the critical properties, liquid molar volume and Antoine coefficients for each species are already available in addition to 3 suffix Morgul's parameters A and B, right. So, first we list out all the equations. Okay. So, in this case T and yi are given. So, you have to find out P and xi. The process that we are going to start can be used for any of combinations, any 2 knowns and then remaining 2 unknowns you can find out, right, for a binary mixture. So, for a binary mixture we are going to do this algorithm development. So, we know that FIV is equals to FIL, that means FIV is nothing but yi phi p, and then FIL is nothing but xi gamma I Fi naught, and then Fi naught, if you, at high pressures we have seen that Fi naught is nothing but phi sat exponential of integral VIL by RT dP, and then if this VIL is independent of delta P, then we can write it as integral VIL by RT dP, we can write it as VIL RT multiplied by delta P, that is P minus PI sat. This is also we have seen. So, now xi you have to find out. So, xi is equals to yi phi p divided by xi phi sat pi sat exponential of VIL by RT P minus PI sat. So, now in order to find out these things, you need to know several things. First of all, pressure is not known here, and then this phi, that is also not known, though van der Waals equation it is mentioned. So, if you remember Figasty coefficient for van der Waals equation of state, so there also pressure term is there. So, this pressure, that is also not known, and then this activity gamma I, so we know it is function of composition of the liquid phase. So, that is also not known, xi, that is what we are finding out. So, temperature is given, so PI sat you can know, and then it is mentioned that the molar volumes etc. are all are given. So, PI sat you can find out because Antoine constants are available, that is what it said. So, these things having the difficulty now, you know, this phi and then gamma I, both of them, you know, having terms which are not known like pressure and then composition. So, this equation if you write for a binary system, it is going to be become a kind of complicated equation to do hand calculation. One has to go for several iterations. So, this for binary system if you write xa is equals to ya phi a p divided by gamma a phi a sat exponential of VAL by RT P minus PA sat, like that. XB also if you write YB phi b P divided by gamma B phi b sat PB sat exponential of VBL by RT P minus P sat, then add them together. So, then we have this summation, this equation number 2, right. Now, we write expression for individual this phi A sat, phi A, and then this gamma A, phi B sat, phi b, and then this gamma b, because it is mentioned that the non-ideality in the vapor phase is described by van der Waals equation. So, corresponding Figasty expressions we can use, and then liquid phase non-ideality can be described by 3 suffix Margol's equation, it is given in the problem. So, for 3 suffix Margol's equation, activity coefficients gamma I expressions we already know. So, we can write down. Saturation pressure can be obtained from the Antoine equation, that is ln pi sat is equals to ai minus bi by T plus Ci, T is in Kelvin and then P sat is in bar. For pure species Figasty for van der Waals equation of state, this is what we have already derived in one of our previous lecture, right. This is pure species Figasty obeying the van der Waals equation, and then there is a pressure term. So, in this pressure term, if you substitute in place of pressure, if you substitute saturation pressure, so then this Figasty is nothing but the Figasty of a saturated vapor phase, right. So, that means under saturation condition, pure species Figasty coefficient, we can find it out as ln phi a sat is equals to minus ln V A sat minus B PB sat by RT plus B by V A sat minus B minus 2A by RT V A sat. Only thing what we have done in this equation number 4, wherever Vi is there we have written Vi sat, and then wherever P is there we have written PA sat, right. Similarly, for phi b sat, ln phi b sat is equals to minus ln VB sat minus B by PB sat by RT plus B by VB sat minus B minus 2A by RT VB sat. Here also in place of what we have done in equation number 4, in place of Vi we have written VB sat, and in place of pressure P we have written PB sat. Remember these equations that is equation number 4 itself is for pure species. So, equation numbers 5 and 6 also for pure species A and B, right. So, when we are say the pure species, so whatever these van der Waals constant A B are there, for they are for the pure component. So, this B is nothing but B A, pure component A, its constant B, and then this A is nothing but A suffix A, that is constant A for pure component A, right. So, that it is explicit, you do not need to write every time. So, and then while second one also we can write this B is nothing but for the pure component B. So, B suffix B you can write like this, and then this A is nothing for pure component B. So, AB, right. So, these are explicit. Now, at this level we already understand what this A and B constant for pure and then mixture, okay, if you are not writing. So, anyway we are writing here pure species Figas-T coefficient. So, phi A sat, phi B sat. So, corresponding A and B should be pure component A and B values. So, this A and B we can find it out from this critical temperature, critical pressure. In the problem it is also mentioned that critical parameters are already available, right. So, for the mixture Figas-T coefficient we have already seen ln phi A is nothing but this expression we have derived, ln phi B is nothing but this expression we have derived. We have derived for a component I in the mixture a generalized one. So, this is what we have written. So, now here this V is nothing for the mixture. Now, B is for the mixture, this here it BAA we have to specifically mention because now it is for the mixture, right. So, BAA is for the pure component A, whatever B constant is there, and then B mixture is that whatever the B constant for the mixture. Similarly, AA or AB whatever written here like this, okay, and then pressure we have to find out, that is not known, that is the reason I highlighted in a red color font. Here in this equation wherever we need probably A mixture and then B mixture. So, this mixing rule we have used, I am not writing them explicitly again. So, further from 3 suffix Morgul's equation we have this gamma A is equals to exponential of A plus 3B by RT x B square minus 4B by RT x B cube, and then gamma B is nothing but exponential of A minus 3B by RT x A square plus 4B by RT x A cube. So, here this x A and then x B are not known, that is the reason I have highlighted them in bold font again. Now, if you wanted to solve that equation number 1, that big equation that we have written. So, what you need to know? You need to know P as well as Xi, both of them are not known, and then we have to do several iterations. So, that for different combinations of P and Xi that equation satisfies. So, rather doing hand calculation several iteration, it is better to have a kind of a small program doing a kind of small programming, and then one can easily calculate. For that we can have a kind of algorithm here. So, what we do? We do not know what is phi A, phi B, because if you wanted to know phi A, phi B, you should know what is pressure. You do not know gamma A, gamma B, because if you need to know gamma A, gamma B, what is x A, what is x B, you have to know, you do not know. So, what we do? We set this phi A, phi B, gamma A, gamma B, all of them are equals to 1, and then T is given, yi is also given, that is ya, yb are given. So, now in this equation you have to find out pressure P as a first iteration, that is ya is given, phi A, phi B we are taking 1, and then phi A sat we have already calculated for a given temperature case, PA sat also we can calculate, gamma A we are taking 1. So, in the right hand side except the pressure everything is known, because phi A, phi B, gamma B we are taking equals to 1 as a first assumption. So, pressure you can find out. Once the pressure is known, then P is equals to RT by V minus B minus A by V square. This equation you can find out This is van der Waal equation. This equation you can find out. This equation you can use to find out V mixture, because no pressure you have already found as part of first iteration, because V mixture is also known is required, because in this ln phi A next step, that is we update actually we update the phi A phi B values. Remember, where the pressure terms are coming only in the fugacity terms are the expression for the fugacity, whereas the composition is coming into the picture in the terms related to the activity coefficient. So, since pressure is already found, so whatever the assumed fugacity coefficients are there, that we will be updating by solving this equation 7 and 8. Right. In this 7 and 8, now after first iteration P is known, and then V mixture you are finding out from the equation of state that is given, that is van der Waals equation of state is there. So, V mixture is also known. A and B constants are known. So, B mixture, A mixture you can find out, and then YA, YB are given, T is given. So, V you just find out. So, everything is known in the right hand side after first iteration. So, after first iteration, what is phi A, phi B you can calculate using this equation number 7 and 8. The equation numbers are same as in previous slides. So, once these 7 and 8 equations are solved to get the phi A and phi B, then equation number 1, that is xi is equals to yi phi I p divided by gamma I phi I sat pi sat exponential of VIL RT exponential of VIL by RT p minus pi sat. This equation number 1 one can solve to get the xi, because yi is known, phi A phi B you just updated after first iterations, P also you have after first iteration, phi sat is already known, pi sat is already known, right. Gamma I you are taking as equals to 1 as a first assumption, right. So, VIL etcetera are known, that is what the assumption of the problem or the statement of the problem says. So, everything is known except the gamma I, which already we have taken as equals to 1 as a part of first iteration. This is all part of first iteration. So, you find out what is xi, right. After finding out the xi and pressure, you can individually check whether the delta P by P is less than epsilon or not. Delta P is nothing but the difference in pressures after 2 successive iterations, right. So, if it is less than epsilon, then you can proceed to the next level calculation, or otherwise you get back to this previous step where you are solving the pressure again, right. So, once xi is known, that means xi xb are known. So, then equation number 9 and 10 you can use to solve this gamma A, gamma B, because xi xb are known, A and B constants are given for 3 suffix Morgell's equation, right. So, now after first iteration you have the updated gamma A, gamma B also. So, now you go back to the equation number 2 to solve again as a second iteration part of second iteration you find out P, what is pressure. Like that you have to continue this calculation until this delta P by P is less than some epsilon value, which is used for the convergence criteria. So, this is how one can make a kind of algorithm to do solving the equilibrium composition for vapor liquid equilibrium problems when both vapor and liquid phases display non-ideality. Okay. You can understand from this that hand calculations are a bit difficult, but however can be doable. So, one last example problem we take now before winding up. Calculate the liquid and vapor composition of a binary mixture of isobutane and hydrogen sulfide at 4.5 degree centigrade and 8.77 bar. So, the pressure is still low, it is not very low, but still low. It is not very high to take that vapor phase as a kind of non-ideal. Excess Gibbs energy can be determined by 3 suffix Morgell's equation with parameters A and B given. So, assume the vapor phase as an ideal gas, that is itself is mentioned, first part of the solution. Second part of the solution, correct for vapor phase non-ideality using Lewis fugacity rule. So, under such conditions you have to find out xi and then yi. Now, here t and p are given, yi and xi you have to find out under two different assumptions. First assumption is that vapor phase is ideal. Second assumption is that vapor phase non-ideality is represented or corrected using the Lewis-Figasti rule. So, data, that is Antoine constants, are given for two components. The corresponding saturation pressure we can obtain by Antoine equations like this. So, first case we take yip is equals to xi gamma I pi sat. Since vapor phase is ideal first case, so there is no phi term is coming into the left hand side here, right. So, if you write for both the components and then add them together, we can have p ya plus p yb, that is nothing but p is equals to xa gamma a pi sat plus xb gamma b pb sat. So, this pi sat are known, pb sat are known, right. Gamma a, gamma b are represented by 3 suffix Margol's equation. So, this they can be written as exponential of this term for gamma a and then exponential of this term for gamma b. This a and b constants are given, okay. Temperature is also given, pressure is also given, okay. So, what is the unknown here in this equation? Only xb, only xb is the unknown. So, here p known given, p a sat we just obtained, p b sat we obtained, a and b constants for 3 suffix Margol's equation are given. So, if you substitute all of these in the above equation and solve, then you will find out xb is equals to 0.47, that means xa is equals to 0.53. So, out of yi and xi you already found what is xi. Now, yi we have to find out. So, for yi to find out, you have that xi gamma I pi sat by p, that means gamma I you have to find out. Since xa, xb are already calculated just now in the first step of this problem. So, gamma a, gamma b you can calculate using this expression now, because xa, xb we already calculated and then a b constants of 3 suffix Margol's equations are given, t is given. So, everything in the right hand side is known. So, then gamma a you can find it out as 1.07, gamma b you can find it out as 1.42, and then you can see now gamma I is greater than 1, that means like interactions are stronger, or the system is showing the liquid phase non-ideality such a way that non-ideality positive deviation from Raoult's law is exhibiting. That is liquid phase showing the positive deviation from the Raoult's law, that is what we can understand from these things. So, once gamma a, gamma b are also known, then you can find out ya is equals to gamma a xa pi sat by p. So, that comes to be 0.118 and then yb is nothing but 1 minus ya, that comes out to be 0.882. So, now yi is also found out. So, the first part of the problem is done when the vapor phase is displaying ideal behavior. Now, second part of the problem, the Lewis-Figasti rule is used to correct the vapor phase non-ideality. So, phi a, phi b terms should be coming for both component when we write this equation yi phi p is equals to xi gamma I pi sat phi sat, that equation if you write for the two components a and b, then you can have this equation. But of course, it should also have exponential of integral vic by RT dp from pi sat to p. This pointing correction, this term should also be multiplied for both of these terms, but we have seen the pressure is small, 8.77 bar. Though it is not very small, but it is small enough, that is less than that is less than 10 bar, something like that. Then we have seen this exponential term induces error less than 4% or something like that. That is what we have already seen if delta p is less than 10 bar. P itself is 8.77 bar we have seen, right. So, this under such conditions what happens, if the delta P is small and then VIC is less than 100 cc per mole, in one of the previous lecture we have seen that this exponential term is going to induce difference less than 4% only. So, that means you can take off this exponential term, or the Poynting correction term can be taken as unit, because its contribution is very small, and then including that term unnecessarily increase the calculations. So, from these two equations what we can write? P is equals to x a gamma a phi a sat P a sat by y a phi a, and then P is equals to x b gamma b phi b sat P b sat y b phi b. This is what we can have, right. Now, in vapor phase, van der Waals equation is it is given that vapor phase obeys van der Waals equation of state, and then Lewis-Figasti rule is applicable in order to account for its non-ideality, or in order to correct for the non-ideality in the vapor phase, that is given. So, in one of the previous lecture, for van der Waals equation of state combined with Lewis-Figasti rule, phi I we have found it like this, but in this exponential term is going to be very small for the case where the pressure is small. So, that we take it as exponential of this term, we take it as 1. So, that we can have only first term. This will also reduce some amount of work. So, phi I is equals to exponential of B I minus A I by R T P by R T, this is what we can have, right. So, this second exponential correction we are taking off because the pressure is very small, 8.77 bar only. It is not very small, pressure is small though it is not very high. So, it may be having some value, but it is not going to induce much error. Exponential term can be taken approximately 1 at low pressures less than 10 bar. So, for this binary mixture from the literature, these A and B constants of van der Waals equation of state are given like this. So, substitute this A, B and P in this equation number 4 to get phi A and then phi B as 0.84 and then 0.943, right. So, in this equation number 4 one more thing is known, and then small a, small b and then P A sat, rather P, if you substitute P A sat in this equation number 4, then you will get phi A sat and then phi B sat, because this equation is valid for the entire range of pressure that we have taken 0 to P, and then P A sat is somewhere in between of this P, right. So, then we have in this equation in place of P, if you substitute P sat, then we will get phi sat, Figasti coefficient of saturated vapor conditions. So, now these values in this equation number 3, except Y A, X A and then gamma A, gamma B, everything are known. So, one can solve for those equations now by substituting these quantities in equation number 3. Equation number 3 is nothing but P is equals to X A gamma A, this P is equals to X A gamma A phi A sat P A sat divided by phi A y A, right. So, this is X A is nothing but 1 minus X B we are writing, P is nothing but 8.77 bar, that is we have written in Pascal, and this exponential term whatever is there, that is nothing but from here to here it is nothing but gamma A, and this is nothing but P A sat, and this is nothing but phi A sat that we just find out, and then this is nothing but phi A. Similarly, for second component also if you write, we have this equation, right. So, now in these two equations what are the unknowns? X B and then Y A, right. Two equations we are having. For writing component A, we have got this equation, this equation when we write for the component A, we got this equation by writing for component B, that is P is equals to xB gamma B PB sat phi B sat divided by phi B YB, this is what we are having. So, here this is xB and then this exponential term is nothing but gamma B, this is nothing but PB sat and this is nothing but phi B sat and this is nothing but phi B, and then in place of YB I am writing 1 minus YA. So, two equations, two unknowns are there. You can solve this equation without any difficulty, and then when you solve this equation you will find out xB is still going to be 0.47 like in the previous case, but YA is going to be 0.14. So, YA is going to be changing. So, YA is 0.14 because now YA, that is vapor phase, we brought in the non-ideality through the Lewis-Figasti rule. Okay. So, this is how you can find out any vapor liquid problem, whether having one phase ideality or both phase ideality or one phase non-ideal or both phase non-ideal, whatever the situation is there, vapor liquid equilibrium problems, corresponding equilibrium compositions you can find out using the problems that we have done till now. Whether it is bubble point calculation or dew point calculation, without any difficulty we can solve them, right, provided required information is available. That is something like Einstein constants, etc., saturation pressures, etc., and then these constants associated with the equation of state, or constant associated with the excess molar Gibbs energy, etc., those kind of thing if you know. So, then you can find out the equilibrium composition of vapor liquid equilibrium problems without any difficulty. References for this lecture are given here, but this is the book that I have followed for this entire lecture. Thank you.